All right, let's get into it. We hear all the time about how amazing AI is with language, but have you ever stopped to think about how these models learn something as basic as the order of words? It's a way trickier problem than you might think, and it has a seriously elegant solution that we're going to unpack.
So it all starts with this weird paradox, right? How can an AI write this beautiful, complex poetry, but at its core, get totally confused by the difference between man bites dog and dog bites man? I mean, the entire meaning is baked into the word order, and for early modern AI, that order was a total black box.
And the reason for this problem, well, it actually comes from the very thing that makes these models so incredibly powerful in the first place, the transformer architecture. See, older models, they read a sentence one word at a time, left to right. But the transformer? It looks at every single word at the exact same time. This parallel processing is crazy fast, but it has this one giant side effect. It basically sees a sentence as just a big bag of words, with no clue what came first.
And this example just nails the problem perfectly. To a raw transformer, the dog chased the cat and the cat chased the dog. They're exactly the same, just a jumble of identical words. All the nuance, who's doing what to whom, it just gets completely lost. Yeah, so they had to fix this, and fast.
So, how did they do it? How did the people who invented the original transformer solve this puzzle? Well, their first fix was pretty brilliant. They basically decided to give every single word its own unique timestamp.
It's a method called absolute positional encoding. And the idea is actually pretty straightforward. You create a special numerical code, a vector, for each and every position. So there's a code for position 1, a different one for position 2, another for position 3, and so on. Then you literally just add that position code to the code that represents the word's meaning. It's kind of like taking the word dog and stamping it with a little tag that says, hey, I'm in position number 2.
And the way they made these codes is just super clever. They used a mix of sine and cosine waves. Yep, the same ones from high school math. Think of it like a clock, but a really weird one with a bunch of hands. You've got some hands, those are the low-frequency waves, that tick really slowly, like an hour hand. Then you've got other hands, the high-frequency waves, that are spinning around super fast, like a second hand. By combining the exact positions of all these different clock hands, you can create a totally unique signature for any moment in time, or in our case, for any position in a sentence.
And what's really cool is that the original creators, they knew they were onto something even bigger. They had a hunch that this method wouldn't just tell the model where a word was, but it would also help it understand relative positions. This quote right here shows they were already thinking ahead to the next big challenge. And that leads us right into the next evolution of this idea. The focus started to shift from knowing exactly where a word is to knowing where it is in relation to all the other words.
I mean, just think about it for a second. When you're trying to understand a sentence, what's actually more useful? Knowing a verb is the 7th word, or knowing that it comes 3 words after its subject?
And that's the key insight right there. For understanding grammar and context and all the complicated ideas we communicate, it's the relationship between words that really matters, way more than their exact spot in a line. This realization really opened the door for a whole new way of thinking.
And that brings us to this truly clever innovation called rotary position embedding, or ROPE for short. And this wasn't just a small tweak on the old idea, it was a completely different way of looking at the problem.
Okay, the fundamental shift is right here. This is the big deal. The old methods were additive. They took the word's meaning and they added a position code to it. ROPE, on the other hand, is multiplicative. It doesn't add anything at all. Instead, it rotates the vector that represents the word.
All right, let's walk through this, because the intuition is fantastic. Just imagine a word's meaning is a single point on a graph. Now, to tell the model where that word is in the sentence, you don't move the point. No, instead, you just spin it. You rotate it around the center. A word in position 1 gets a tiny little rotation. A word in position 5 gets a much bigger one. And the magic here is that the relationship between any two of these rotated points now automatically encodes their relative distance from each other, which is exactly what we were trying to achieve.
And this little rotation trick, it comes with some massive advantages. For one, it makes the model super flexible, so it can handle sentences that are way longer than anything it saw during training. It also has this natural decay built in. The connection between two words gets weaker the further apart they are, which is exactly how our brains process language. On top of all that, it works beautifully with all the new super efficient model architectures.
Okay, so that's some pretty cool math, but what's the real-world impact? I mean, why should we care about rotating vectors?
Well, the proof is in the pudding, right? Just look at the data. This table comes straight from the paper that introduced ROP. Check out the row former model. It's not just outperforming the other models, it's doing it while handling text that's twice as long. So it's better, and it works on way longer stuff. That's a huge win.
That jump in performance over the next best model is about 1.5 percentage points. Now, I know you might be thinking, 1.5%? That doesn't sound like a lot. But trust me, in the world of these giant AI models, where every single fraction of a percent is a brutal fight, a 1.5% gain is a massive leap forward.
And that's really the main takeaway here. This idea, this little trick of rotating vectors to encode word order, it isn't just some forgotten detail in a research paper. It is a critical, absolutely fundamental ingredient inside many of the most powerful language models that you and I use every single day.
So it kind of leaves you with this final thought. If reinventing something as basic as how we represent the order of words can lead to such a huge breakthrough, it just makes you wonder, right? What other simple fundamental ideas in AI are we all just taking for granted, waiting for someone to come along and give them a whole new spin?